Hello, this is Tuesday, October the 29th, and I'm going to take a few minutes and walk us through Chapter 8 of Healey. This is a change that from what we were doing in Chapter 7, which I'll talk about here in a second, how that change is. I have a diagram here on the board to kind of walk us through that. Here we are in principle doing something very different than we did in Chapter 7 before we get to the other part of it. If you'll recall in Chapter 7, we did not know what the population parameter was. We were going from population, we couldn't go to the parameter, so we would come down with a sample and then representative unbiased sample, do our analysis of the sample to get a statistic, and then because we had representative sample, it was unbiased, it was a sample of sufficient size, you know, all of that conversation we've had in previous videos, and in Healey, then we knew that the statistic that we had was a fairly efficient or accurate estimate of the parameter, and we would have found something very similar had we gone directly from the population to the parameter. But because at a million people, it's hard to ask a million people those kinds of questions, we draw a sample down to say 1,000. So we also recognized that that one sample is a single point estimate, and let's say it's a sample size of 1,000. If we were to draw down 100 samples of the same size, each would have 100 different individuals in them, and or each of the 1,000, if we did 1,000 samples of the same size, if we drew them down 100 times, each one of those would have probably 1,000 different people in them. So we would expect that if it were average age we were getting at, we'd have an initial average age in our empirical sample that we did, and then any ones that we would follow after that, probably there would be some variation in the average age because the composition of each of those samples is different. But we know from one of the theorems in Chapter 6 that if we're over 100 in the sample size, then we're pretty good at estimating what that parameter is. So we can figure that the variation would be just a small amount, say around the initial value that we got, enclose it in kind of a range of high means to low means. Remember, these are 100 different means from 100 different samples. So we get a distribution of means, and because it's 100, it takes a normal curve. And that normal curve, if you remember from Chapter 7, is that sampling distribution, which is in the center. We have the distribution of the sample, our empirical one, and then we have one that we imagine up there in the population that is a normal distribution because of the size of the population. And we use that middle one. It's an abstract, one that we don't ever see. It's a theoretical model that we use that to kind of filter through to do confidence intervals, so that we can say with the confidence interval of Chapter 7 that using a confidence interval of 95%, then we could say 95 out of 100 of those samples are within these two standard errors plus or minus the mean. That would be the size of our net. And we would try to capture the true parameter inside that and be reasonably comfortable with what we had. And with the idea that that other 5% distributed in the two tails is a possibility that we did not catch the parameter, but that's okay. I mean, not okay, but it's okay. Now we're willing to take the chance of 5 chances of error out of 100. So that Chapter 7 was about trying to identify a parameter we don't know. Chapter 8 and Chapter 9, which we'll do video next week, Chapter 8 we know the parameter. And so what we're wanting to do is see in our study if the parameter that, the finding of our study is different than the population parameter. And if you look at here, here's Chapter 7. And what we're looking for is something within two standard errors. They are standard deviations, but remember, this is that distribution of sample, or the sampling distribution rather. Here we call that normalcy and these vertical lines as standard errors to differentiate the standard deviations that we see in the empirical curve down here. Same process. Math is a little bit different, but basically the same principle. So in Chapter 7, by definition, we're saying anything that's within these two standard errors, minus 1.96 on the left and plus 1.96 on the right, anything that's within these is similar. So even though right here we might have our mean that we got from our point estimate, we recognize that it would vary a little bit because the composition of each of those samples would vary a little bit. So the average age, let's say, would vary a little bit. And so we bound our net, we construct our net by two standard errors above or below that estimated mean that we got from our empirical sample. And so we're pretty sure that somewhere in there, 95 times out of 100, we're going to have that parameter that we're interested in inside here. Similar. Now, when we come to Chapter 8, here we're talking about dissimilarity or difference, not something that's the same. We're trying to demonstrate that what we're doing with our sample, the finding is statistically significantly different than the parameter. And they've got some interesting illustrations at the opening of Chapter 8. You take just number 1 in that introduction, 789 older residents, it's a sample. The issue here is whether that sample, their victimization rate, is statistically significantly different than the victimization rate of those in the larger population. Now, if we're in social sciences, social work, criminal justice, whatever we might be in, where we're interested in victimization rates of the elderly, if our idea is to develop an intervention that enables the elders to understand how to protect themselves against crime, then in order to get the money, shall we say, from the county judge or wherever we're going to get it, some funding source, we have to demonstrate that that experience of the elders in our neighborhood of interest to us or the subcommunity of interest to us, that rate that they're experiencing is statistically significantly different than the overall rate. If we can demonstrate that, then we have evidence for why we need to bring some funding in to do some crime education for the elderly. And that's the important difference in a way in demonstration between Chapter 7 and Chapter 8. Chapter 7, we don't know what it is, we're trying to estimate it. Chapter 8, we know what the parameter is, but we're trying to show where our intervention is happening, be it whatever that intervention is, whatever the social theme we're intervening, that rate or characteristic or mean or proportion of the subpopulation of interest to us, that is our sample, that is significantly different than the overall rate of the city. For example, here in San Antonio, maybe we're interested in the Hispanic elderly on the west side. And so we draw a sample of the Hispanic elderly on the west side with the idea that the crime rate perpetrated against Hispanic elderly on the west side is very much different than the crime rate overall in the city. So we take a sample of the elders, Hispanic elders on the west side, calculate out the rate of crime with the idea of being able to show that the rate is dissimilar from what is the overall rate. Now, here, just kind of looking at the diagram, I think Healey does this very well. You'll see how he does this on figures on page 188, 183, and over on page 191. A lot of demonstrations like what I do here. I think he's very effective at how he draws these things out literally as well as figuratively. So here we've got a normal curve again with the same two standard errors, 196 and 196 being minus, of course, and this being plus. And here we know what the parameter is. So what we're trying to show mathematically, that the value of the parameter, that rate for the county at large, let's say, is statistically significantly different in value than the value that we have in terms of a rate for our Hispanic elders on the west side of San Antonio. So it's called the null hypothesis. The null hypothesis is that the value that we see in our sample, that statistic, is only trivially, the difference is only trivial from the value that we see in the parameter and the population. Our research hypothesis is that it is statistically significantly different. And the whole process that we do in Chapter 8, and you'll see in Chapter 9, if we follow that 5-step sequence and using the correct formula, we'll be able to demonstrate mathematically whether or not, and hopefully so, that what we see in our sample is statistically significantly different than what's up in the population. That being so, then in the case of the elderly and needing some funding, let's say, for our project to do some crime education, we now have evidence that that funding by the county judge or wherever is warranted because the rate for the elders is much higher, statistically speaking, let's say, than the overall community. Now, whereas before, this is similar, we didn't even think too much about this in Chapter 7. Here, it still remains our boundary, as it did here, but instead of being interested in what is similar on the inside, we're interested in what is dissimilar on the outside. So what we're hoping when we go through the formula, that the value for our statistic that we see will fall in one of these, what I call rejection zones, or the book calls the critical region. These boundaries are defined by critical values, and they're described in a couple of places here, and we'll walk through them in a minute. Those set the boundaries. Anything outside is a critical region. If when you calculate out one of those formulas in Chapter 8, and you get a z-score, which would be your critical region is 196. Consensus is, for most part, most of the studies that we do in statistics, it's 95 out of 100. You might have 90 out of 100, you might have 99 out of 100. You can walk your way through that. There's plenty of illustrations there. But for the most part, we say 95 out of 100. If the homework doesn't say do 90 out of 100 or 99 out of 100, always do 95 out of 100, because that's 95 times out of 100 what you'll do out there in the community, in the world. So what we're looking for then, when we get, this really should be a, the critical region is 1.96. So what we're looking for is, that's the critical value. What we're looking for is the observed z. You're going to do an observed z, and you want that observed z to be larger or equal to the critical value of z. The critical value is defining the boundary line. So in that sense, if the z then falls somewhere out here or over here, then you mathematically have the basis for your decision to reject the null. Simple as that. Sort of simple, right? Well, you've got 5 steps to walk through, and if you do the math right, the process itself will tell you what your decision is. So that's the basic principle. We establish the null here in the center with the idea that if we can show a z-score larger than, and over here is larger than, if it's minus 2, that's larger than minus 1.96. If it's 2 over here, that's larger than 2.96. Now, one other thing I want to think about. When we look at these, you got to go back a little ways to, I don't know, Chapter 4, Chapter 3, somewhere in there, when we were talking about probability distributions. When you look at one of these, you've got to remember that in the background there are bar charts. And just go back to Chapter 2 and 3 and remember how we talked about that. And so that these lines are polygons, so that the bars of the bar chart are higher here because there's greater frequency in those bars, and the bars out here are smaller because there's lower frequency. So in the tail, there's the numbers are smaller, I mean in volume, and over here, but there's a whole lot in the center. And that's why we can say similar here, and why we can say dissimilar here. The other way, in other words, the values that are out here in the tails are very much different than the values that are in the center of the distribution. And just walk your way back through the chapters and reason your way through that. The other way to think about this is probability. And we did talk about this early on, I think Chapter 4 or 5, about the probability distribution. We got a frequency distribution, we got probability. So if we look at what's out here in the tail, one way to think about this is that as you move from the center, things become less probable. The values in here, look at this mountain of data, are very probable. But out here in the tail, where the data are fewer, those are improbable. So in that case, as you move out towards the tail from the center, things happening that happen out there are improbable. They're not likely to happen by chance. In here, you could pull out a good value by chance. Over here, the values out here are so improbable that they're not likely to have happened by chance. Now that is an assumption, a vital assumption of statistics of where we are right now. These are improbable. So, if then we get out here in the rejection zone, we've defined anything that's outside these as improbable, not likely to happen by chance. So if we get an observed z that's out in one of these rejection zones, then we can say we reject the null because it's very improbable, very unlikely that the values of our statistic represented by the z-scores out here in one of these rejection zones, very unlikely that those would have happened by chance, and so we conclude that they are substantively of value, and our procedures show that since my z-scores are out there, we can reject the null with some confidence that we're rejecting it correctly. And that's really what this is all about. And I want to point out the importance of this in terms of programming, community-based programming and all, because when you want to get the evidence for why you need the program, when you go before a funding source, this provides very solid evidence of why you need the funding to represent, say in this case, we were talking about the elders on the west side. Okay, so if you fall in the rejection zone or the critical region, if your observed z is larger than your critical value, your observed value is larger than your critical value, and for the most part 1.96, then you can reject the null with some confidence. Now always remember, these are all probabilities. It is 95 out of 100. So if you reject it, it doesn't mean absolutely that the null is incorrect. It just means that it's highly improbable that what your conclusion is incorrect. Because if it falls out here, these are improbable events out here, not likely to have happened by chance, and that's the assumption that allows us to carry out this exercise. Okay, so let's take a look at some things in the chapter. I think you've learned that Healey's pretty straightforward, and it doesn't really require a lot of board work, although it's fun doing board work, I have to admit. But I think you can, in terms of doing formula and things like that. Let's take a look at the first one, overview of hypothesis testing on page 180. Here we have an interesting situation. You can see on top of 181 that there's a sample of treated alcoholics. They've gone through a rehabilitation clinic, and now their average number of days is 6.8 per year of being absent, whereas the community value is 7.2. Well, when you look at that, you think, that seems not much different, and it doesn't seem that way. But what we want to demonstrate, is that a trivial difference or is it a statistically significant difference? And so when you come over here, you'll see on page 182 they talk about the null hypothesis, the principle of that. And you'll see that they express there as 7.2 days per year in the middle. Now, what I suggest is you don't worry about this notation of HO colon mu equals. Put it in the English. Say that the null hypothesis is that the 6.8 and 7.2 are basically equal. That if there's any difference, there's only trivial. Just put it out in the language. If you go before the county judge or anybody and you're looking for money, you probably need to put it in a language that we all understand and don't be putting it in stats notation. So, and besides that, it'll help you kind of get this thing ingrained in you. All right, so you can see what the null hypothesis is down. There's some italics. If the odds of getting the observed difference are less than 0.05, 5 out of 100, we will reject the null hypothesis. So what we're saying here, the odds are 5 out of 100 that we're making an error if we reject the null. And in social sciences, we're willing to accept that as an error. Now, if we were I worked at medical school, and if there were, like in surgery or some medical procedures over there, 5 out of 100 is not a very good error rate. Probably not even 1 out of 1,000. Maybe 1 out of 10,000. You can imagine in school that teaches surgeons, the last thing you want is 5 errors out of 100. It's pretty obvious. So their p-values, their probability values, are going to be much tighter than ours, but the processes at arriving at them are the same as what we do in this book. The statistics over there are the same. It's got a little different kind of notation, or not notation, but different kinds of books, slightly different language, but the basic underlying process of statistics is exactly the same, whether you're in business, at medical school, in the social sciences, or wherever you are, psychology, they're exactly the same. Now, the assumptions might be a little tighter, as in medical school. All right, so here you can see, over on the right-hand side, about halfway down, you see something that looks familiar to you, the z-score. Notice that the sampling distribution, figure 8.2, 7.2 is in the center, and 6.8 is on the left-hand side now because it's smaller than. Remember, when we're doing these normal curves, the left-hand side of the normal curve is negative because all values to the left of the center of that distribution are smaller than. Any values on the right-hand side of the center of that distribution are larger because all the x's and values out there are larger than the mean. So when we see that at 6.8, we would position it in our turtles. You want to draw your turtles like you did for chapters 5 and 6 and 7. You want to draw your turtles for chapter 8 so that you get yourself aligned up spatially, if you will. I think that spatial orientation is very helpful and help assuring that you're getting the right answer. Now, when you come over to page 184, you see there that formula 8.1 is the formula we're going to use when we're talking about means. You can see the z equals the mean minus the mu over the standard error divided by the square root of n. Now, the sigma is the population. What we get when they give us the mu, they're giving us that, they're giving us the standard error. So they're giving us things that we didn't have in chapter 7. We have them in chapter 8. Now you have to remember, they're giving it to us, but if you were out there in the world, you'd have to first start with chapter 2, and describe all of the internal dynamics of these variables. Go to chapter 3, do the central tendencies to get your mean. Go to chapter 4 to get your standard deviations. Chapter 5 to begin to visualize your z-scores. Chapter 6 to think about your sampling. Chapter 7, maybe do some confidence intervals perhaps, or you move right to chapter 8 where we are now. So in order to get to this formula right here, if we weren't in a textbook environment, you would have to do all the previous chapters of Healey to get at the values that are in that formula. So I think you get the drift, right? All right, so here you see how that plays out. Z equals 6.8 minus 7.2 over 1.43 divided by the square root of 127. And you go down through there and the z equals minus 3.15. So here it is, 1.96, and it's way out here. It's very much larger, the observed value, than the critical value. So we can reject the null and say what difference that we see, although it looks trivial, is statistically significantly different. And consequently reject the null. And then we would conclude, you always want to conclude with a statement, when we reject the null, it does appear that the rehabilitation plan in that clinic works, or something along that line. To put it back into the statistics into context. All right, let's look at 8.3, the 5-step model for hypothesis testing. Every one of your homework problems requires a turtle and requires step 1, 2, 3, 4, and 5. You must do these steps to get full credit for your homework. You listening to what I'm saying, right? If you want full credit, turtles and 5 steps. Every one of the problems. All right, let's look at this. Step 1, making assumptions. Now you go down about 3/4 of the way and you can see model, random sampling, level of measurement, interval ratio, sampling distribution is normal. Now if we were doing this and we were colleagues and we were building this thing, we would want to make sure that we had randomly sampled, we've gone through that, chapter 6, and that we've got some normalcy in our distribution. In other words, we've got a sampling size over 100 to take on a normal distribution, more or less, or even better if it's over 100, and that the level of measurement is interval ratio. Now that's a critical statement because some of the things that we're going to be doing are proportions. Proportions are derived from categorical variables. So that level of measurement is interval ratio, or in a problem we'll look at in a minute is categorical, will trigger which one of the formulas in this chapter you're going to use. You have to be sure you're specific to your interval ratio, your level of measurement, that you're specific to that when you pick the formula to calculate out what you're going to do. All right, so you want to state that model, even though you're repeating it over and over again in these problems, do it anyway to get full credit. All right, step 2, you state the null hypothesis. And you can see over on page 186 that there it is again, what we saw a minute ago, but put it in the King's English. Say that the null hypothesis says 6.8 and 7.2 are essentially the same, the difference is only trivial. And then you can state the research hypothesis and say, well, the research hypothesis is those two are different, and statistically significantly so. Just put it in English. All right, so there you would state your null and your research hypothesis. And then when you get to step 3, we establish the critical region. What is the boundary that we want? And generally, the boundary is like what they did here. You can see down there a little ways, z critical plus or minus 1.96. For the most part, that's what we do in statistics, 95 out of 100 or an error rate of 5 out of 100. That bounds your critical region. Everything outside is, by definition, significantly different than the null, which is in the center here, where the green piece is. And then that creates your region of rejection. If it lands out here, bingo, reject the null. If it lands in here, the value is similar, and you cannot reject the null. Too great a chance that if you reject the null, you'll be making an error. So follow the mathematics, do the mathematics correctly, of course, not always easy for me either. Do the mathematics correctly so that you can see if you get a z observed larger than these critical z's, then you can make your decision to reject the null. All right, now this is a sampling distribution, is a z distribution. We'll look at that. This is true for large samples that have means and large samples that have proportions, but it's not true for small samples for means, and we'll look at that in a minute. You can see the alpha is 0.05. So then we establish our to compute the test statistic. In step 4, we do the formula that we saw a minute ago. Formula 8.1 is what you would do in step 4 to derive your observed z. And then you come down to step 5, and they didn't put it there because they already did it on a page or two before, on page 184, but you would put it in that step 4. And then in step 5, you see the z critical plus or minus 1.96. The obtained is minus 3.15. I would express it like this. Observed, I don't see my, here it is. The observed value is larger than the critical value. Consequently, I reject the null. Lay it out so that you can see it real easily. Where you put it just like that, z critical and z obtained, you can see that it is, but put it in a formula like this or a statement like this. The observed value is greater than or equal to 1.96. And they say, therefore, I reject the null. The rehabilitation system seems to work. Okay, and there you can see again on page 186 what Healey does so well, I think, and that's the one step at a time to walk you through this. Okay, now let's look at page 8.4. And then he's got a nice table of 8.1 that talks about what you do if you reject the null or you don't. Pay attention to that. On 8.4 is kind of a conceptual thing we have to talk about. Now, we're in a highly competitive environment, and you and numerous others are trying to get money from the county judge for projects. And really the last way you want to go before any funding source is say, I'm not real sure which way this is going to go. The rehabilitation might work, it might not work. Give me some money, and then I'll see if I can find out which way it goes. Now, there may be some times when you need to do that. But generally what you're going to do, because you're in the business, you're going to do a literature review. Yes, a literature review. It's all, it's not just something you do for a methodology class to get a grade. It is a central piece of any research and practice project, the literature review. It is to compare what you want to do with what your peers out there have done, and to pick a few things from them that might be of value in the generation of your own project. So from your lit review, you're going to have an idea that your statistic is larger or smaller. I'm saying before you do it. You're going to have, say for example, the one that we did a minute ago about crime rate. You probably will know from literature review and your experience of working in the West Side that there's a higher rate. You'll have a gut instinct, and then you can capitalize on that gut instinct with a lit review and focus groups and conversations, qualitative methods to kind of really flesh that out. And so that when you go before the county judge, you can say, look, it's not that I don't know which way it's going to go. What I can tell you, Judge, that I'm going to be able to demonstrate to you that this is higher than, in the West Side, the crime rate, than the city at large. You'll use a one-tailed test. Excuse me. So here again, what I'm saying is, what you always want to do out there in the world, for the most part, not always, but 99 out of 100, you're going to want to go at the funding source in your practice or your research project with a one-tailed test, because you're going to know which way the thing is likely to fall. You're going to have a pretty good sense of which way it's going to go. Don't be wishy-washy out there in a competitive environment for funding. Stick your chests out and say what you think. So what that means is, what we would do in this case, we wouldn't have used 1.96 if we had a one-tail and we knew this is 6.8 and this is 7.2. We do 1.65, which is a one-tail 95 out of 100. And there is a table in here on bottom of 190 where you can see how that works. So then what we're looking for is an observed z that's larger than 1.65. Now that's an interesting thing, because it takes a larger z to beat out 1.96, let's say, than it does a one-tail 1.65. Here, if you had a 1.7 over here, it'd be similar. But here, if you've got a 1.7, then it's larger. So there are some mathematical, shall we say, benefits to doing one-tail, but it also is conceptual, because it strengthens your proposal and your practice if you know, reasonably certain, which way it's going to go, and you stick your chest out and demonstrate what you have said. So generally, unless the problem says, if it says do two-tailed at 90, then that's what you do. If it doesn't say whether to do 95 or 90 or whatever, then do 95. If it doesn't say to do two tails, then do one tail. And then be mindful that when you're looking at the mathematics of this, if you get a negative value when you subtract the mean, then you're going to be on the left-hand side. And if you get a larger value when you subtract your statistic from the population parameter, then you're going to be on the right-hand side. So you just want to remember that part. Okay, so do one tail as best you can. All right. You can see there, when you come over in the bottom of page 190, how they've laid that out. There you see two-tail 1.96, like what I did up here, and then a one-tail plus 165 or minus 165. Again, 95 out of 100 is generally 95 out of 100 times what we're going to do anyway. So get the hang of doing that. Now, let's selecting an alpha level. This is conceptual a little bit. And I think you're not going to have anything on the homework on this part. I'd like to come back to this in Chapter 9, because Chapter 9's video is going to be a little shorter because we're laying the groundwork for that. It's basically the same as here. And let me come back to the Type 1, Type 2 errors next week. All right, go to page 195, and you'll see that here we're talking about sample sizes that are less than 100. And you notice at the top, there's a diagram there where you've got the classic looking normal curve for 100 or greater, and then you've got a flatter normal curve which represents a distribution of less than 100. And when you look at that, you can see how they overlay one another. You can see the probabilities are distributions are very different in a sense. The out here, the tails are small, clearly improbable. But when you do that normal, the normal curve for something less than 100, that comes out. It looks more like this, and so all of this becomes fuzzy. You know, it's probably less probable than here, but not quite so improbable as in a more normal curve. So we have to do a little bit different statistical procedure with that, and we'll walk through that. It's called the student's t-distribution because back about 130, 40 years ago, whenever all this was taking place in the 19th century, they were doing z-scoring like we were doing here for large sample sizes, but there are small samples too that weren't being taken into account, and the mathematics weren't working quite so well, just like you can imagine applying what we were doing a minute ago when you've got this kind of fuzzy, not so clear, distinguishable improbability on these tails. So there was a student in this very well-known statisticians class who solved the problem, but he didn't want to show up as prof, so he published it as the student's t-distribution, and it spread like wildfire. It solved a problem. And even though that student is well-known now and became a well-known statistician, it has remained as the student's t-distribution. And I think it's cool because it lets you know that I may be the prof and you're the student. You have all the capacity that I have to do this, and probably even better. So keep your mind open and challenge yourself and create your own student's t-distribution, if you will. All right, so what you'll see in this is still, again, basically the same process. Let me point out on application 8.1 on page 196, there is a demonstration of what we would do if we were doing this on a chalkboard or whiteboard. Clearly stepped out. Step 1, 2, 3, 4, and 5, the formulas and everything. This is what each of your problems will need to look like. Model them on this application 8.1 all the way through, whether we're doing this one, the t-distribution, or the one we're going to do on probability or proportions in a minute. All right. Now, we have a t-critical, same principle as here, but it's a little bit different. I want you to take a look at the z-distribution is Appendix A, and we're familiar with that from Chapter 5. If you go to Appendix B, you'll see a distribution of t. It's only one page, and that's because the values are smaller, 100 or less, whereas over here on page 486, the values could be infinitely in size, shall we say. And you want to pay attention to the structure of the table. Degrees of freedom, we'll talk about that in a minute. As you go down the left-hand side, that's the sample size of your small sample. That's a sample size minus a number of values, and we'll look at those in a minute. So you find your degree of freedom, and then you'll see there are two tiers at the top. There is a one-tailed test at the very top and a two-tailed test tier underneath that. So if we're doing, say, a two-tailed 05, then, and say our degree of freedom is 25, we find 25 in the far left-hand column and go over until we come under two-tailed test 05, and we see that the t-critical is 2.60. So we need something larger than 2.06. If it's a one-tail, 0.05, then we would do 25, and you'd see that 0.05 is up at the top tier, and you fall down that third column over, and it's 1.78. That bounds the critical region, just like we did with the z. So be mindful of that. Now, let's talk for a moment about degrees of freedom. One way maybe to demonstrate this would be to, if we had a value, say, as you can see this, of 10, and up here is a 3, and we have two slots, and this is the sum. We have 1 degree of freedom in this particular exercise. For example, if I say this is 4, then that's automatically, since that's 7, that's automatically a 3. If we take the degree of freedom that this is a 5, then this automatically becomes a 2. If we say that this is 7, then as a degree of freedom of 1, that we put a 7 in here, then this automatically becomes a 0. Now, what we're talking in the degrees of freedom in this homework in Healey is 100 or less. So we're talking about a stack of values here. So when they say you've got 23 degrees of freedom, there's a lot of values you can put in here until you finally get to that last one that's fixed, and then you've got what you've got to do with your statistics. But this basically gives you an idea of what degrees of freedom. Right now, with that, saying we need two values, we got 1 degree of freedom, not 2, 1 degree of freedom, because as soon as we pick a number randomly and put in 6, then that automatically defines this as a 1. We have a degree of freedom to pick any value there, but once we have the remaining value becomes fixed. So that's kind of an illustration of how that works. And so let's take a look at how they do the degrees of freedom. And notice on page 199 in step 3, the sampling distribution is a t-distribution. Alpha is 0.01. Two-tailed, well, let them do it. Alpha is 0.1, which means it's 99. It's okay. We know that as a rule out in the world, we're going to do 95 with an alpha of 0.5, but it's okay. We'll let Healey do this because we want to learn how the process works. The degrees of freedom is n minus 1. Now you go back over here on the left-hand side, or the page 198, you can see that the n is 30 under commuter students. And so we do 30 minus 1 is 29. And so let's go to, and they're doing a two-tailed test. Let's go to distribution T. We got an alpha 0.01, two-tail, all right, and a degree of freedom 29. We go to appendix B, and we go down till we get a value in the far left-hand corner, or far left-hand column, degrees of freedom, till we get to 29. And then we go to 0.01 what are we looking for? Two-tailed test. So we're going a two-tailed test, 0.01, and we go on over, and there you can find 2.756. And so that's how they got that value. That then becomes the boundary outside of which the t value is larger than the t critical. That 2.756 is the t critical, so we're looking for a t value larger than the t critical, the t rejection zone, just like the z rejection zone, and then we can decide whether or not to reject the null. And so here we see a t critical of plus or minus 2.756, but when we go to step 4 and we do all the mathematics, we get a t obtained of 1.122. 1.122 is smaller than the t critical, so what would we do with the null hypothesis? Yes? What? What would we do? Would we reject the null, or would we not? I hear one or two say, we'd reject the null, but I think I hear most people saying, we would reject the null, Dr. Blanchard, because that t obtained is smaller than the t critical. And yes, that's exactly what you would do. And then you would say that commuter students' GPA is not that much different than the residential students. The difference that we see is only trivial. Okay, one other thing before we close out, and that's on page 200. Whereas before we had a large z, or a large sample size with a mean, and then a small sample size with the mean, which is the t distribution, the first is z distribution. Now we got hypotheses for single samples large. You'll notice that this is also a z distribution, so we're talking about a sample size of 100 or larger. And there you'll see on page application 8.2 how that's carried out. Step 1, 2, 3, 4, 5, much better than I could do on this little old whiteboard standing behind me on the stand. You'll see the formula on the bottom of page 200. A little bit different, but hopefully not too scary. And then you lay it out and use that example that they have there. Always remember, I shake my finger at you, always remember you may not be given a proportion, but they may give you like 0.34. They may give you 34%. And then you got to back up and say, wait, knock that percent out, take it back to the proportion of 34. Don't put a percentage in here. The other thing that will happen to you, they'll say 127 out of 422. Don't put 127 in there. Divide 127 by 422 and get the proportion, and put the proportion in there. You have to be careful about these things. Something minor like that, seemingly minor, will get you a very bad answer. And nobody wants any bad answers, do they? Absolutely not. Pay attention to application point 8.2, and you'll see how that works. Okay, now I think that's enough for now. I thank you very much for the work that you're doing out there, and you've gotten an email from me, and we're kind of spreading this out for a little while because some events that are going on that I'm taking care of or participating in. So the homework chapter 8 and 9 are not due. It's not due until 2 weeks from today, actually. And we're extending chapters 8 and 9 work until next Thursday of next week. I think that's the 7th of November. And following that class period, I'll put a video out on chapter 9. Some of it will be very similar to what we just did. Chapter 9, I'll go back and talk about those type 1 and type 2 errors. So thank you very much, and Talk to you later.